The word linear just gives us an idea of the type of motion that we'll be dealing with. This is going to be motion in a straight line at the beginning. Yeah, so momentum is simply going to be denoted by letter P. Momentum is just a product of mass and velocity. So this is your momentum. That's the M. Then we have mass, which is supposed to be in kilograms. This is our mass in kilograms. Then we have velocity, which is in meters per second. Now we can have initial momentum or final momentum. So initial momentum, meaning we're using mass and the initial velocity. You can have final momentum, which is just mass and the final velocity. Then we can also get the change in momentum. So delta P, the change in momentum is just momentum final minus momentum initial. So just subtracting these two. This is mv minus mu. Then this change in momentum that we're discussing is going to be called impulse. Whenever you find the change in momentum, this is the same as what? Impulse. That's what you have. So we can just say impulse is simply mv minus mu. Now, you know what acceleration was from your linear, your motion equations. This is simply, so if I may say this and write it like this, let me just write the impulse. Impulse denoted by letter I is mass, final velocity minus initial velocity. I just factorized our mass here. Now remember, acceleration was equal to v minus this is v minus u over t. This was simply our acceleration. This is what you had. So meaning, where there is v minus u, I can just replace by at. Is this okay? You're seeing this?
Yes, I am seeing this.
So,
okay.
Yeah, so meaning impulse is the same as mass times acceleration times time. Now, we know what ma is. Remember, force is equal to mass and acceleration under the second law of Newton. So we can replace it here, meaning impulse is the same as force multiplied by time. So just right here from momentum, we've created three equations. So the first equation, we said impulse is just mass times velocity. It can either be initial or final. Then the change in momentum is what we call impulse. That's the second equation that we've created. Then we've also made the third version of impulse, which relates force and time. So we're saying impulse is directly proportional to the force and the time. Now back to our momentum. We just said momentum is this. Remember this. You also know that kinetic energy is equal to half mv squared. Then we can modify this equation for it to look exactly like this guy here. So I can first of all square both sides, meaning this is going to be p squared, m squared, and v squared. Then I multiply both sides by half. So I'll multiply, or rather I'll divide this side by m, so that I just have p squared over m is equal to mv squared. Then introduce half this side, introduce half the other side. This here is kinetic energy. So we're saying kinetic energy is actually related to momentum. Kinetic energy is the same as momentum squared over 2 times the mass of that particular object. Is this equation okay?
Wait, repeat again how we got the 2m down.
Okay, so here from here dividing by m, you're okay, right? Dividing by
yes.
M. So now we formulated to say p squared over mass is the same as mass v squared. We're trying to design the kinetic energy formula. That's what we're trying to design. Yeah, we want to create this guy. So what is only missing from the right hand side for it to be exactly like the kinetic energy formula is us multiplying everything here by half. So that's the main reason why I've also multiplied this side by half. What you do on the right, you also do on the left.
Okay. Okay.
So now this has become kinetic energy. Then you know here 1 times p squared, that's going to be p squared. Then 2 times m, that's where the 2m came from.
Oh, okay.
Exactly. So they like this under multiple choice questions. It never misses. I think every year they always ask about the relation between kinetic energy and momentum. This is always the relation. This is how they are related. So kinetic energy is equal to momentum squared over 2 times the mass. And this just explains that whenever something is moving, an object in motion is the one that has momentum. A parked car cannot bash you, isn't it? Because it doesn't have momentum.
Yes.
And then you notice that mass and velocity, mass is a scalar, velocity is a vector, implying that the bigger the mass, the more the momentum. So someone who is bashed by a car, the impact is going to be more as compared to someone who is bashed by a bicycle, because the car has more mass. And also the velocity, the more the velocity, the more the momentum, because there is a direct proportionality between them. And the reason why I said we are multiplying a scalar and a vector is because since velocity is a vector and you're multiplying it with a scalar, the answer whenever you multiply a scalar and a vector is supposed to be a vector. So this implies that even momentum as well is a what? Is a vector. Yeah, so meaning we can have momentum in the x-axis using velocity in the x-axis. We can also have momentum in the y-axis using the velocity in the y-axis, meaning the final momentum is going to be the momentum you got in the x squared, the momentum you got in the y squared, and the direction of that momentum can be gotten the same way we are doing under vectors. It's like getting the resultant and the direction. So this can also apply because it can be resolved into x and what? And y. Is this okay?
So you're saying vectors comes back here again?
Yes, vectors come back here. Yes, they will come back here. Yes, not for the first part, because here, according to the title says linear momentum. So at first, we're going to talk about this in a straight line. So everything is just moving in the x-axis. Yeah, but I just want you to take note that if something is moving in the negative direction like this, it simply means that there is negative momentum.
Yes.
We can have positive or negative momentum. That's what I'm just trying to stress. And that simply gets back to our vectors. Later on, we're going to be talking about momentum in 2 directions. If something is, let's say, moving like this, the mass is, let's say, 2 kg. Then the velocity is, let's say, 6 meters per second at an angle of, let's say, 30 degrees. I ask you, what's the momentum here? You have to get the momentum in the x, which is the x component of the velocity, which is just 6 cos 30. This is the Vx. You have to get the Vx. So we multiply the mass and the Vx. Then again, you get the y component, which is the mass and the Vy. So once you get your x and y component, you can now get your resultant momentum, which is just going to be just like Pama vectors. Yeah. Yes, we're going to be doing this. Is this okay?
Yes, it is okay.
So we're saying momentum, we've established one thing to say momentum is a vector. Why? Because it depends on velocity, which is a vector as well. And we're going to discuss this in a linear motion. So maybe just a summary of the equations we've discussed so far, the equations I've given you so far. The first one, we said momentum is mass and velocity. Then we said, so meaning this implies we can have initial momentum, mass and that, or final momentum, which is mv. Then this gave us the change in momentum, which is just called impulse, which is the same as mv minus mu, which later on changed to become force times time. Yeah, that's what we got. Then the third one, the third formula is where kinetic energy is the same as momentum squared over 2m. So this is what we are having. These are the only 3 equations with 3 sets that we've discussed so far. Now, why are we learning this? Why are we learning momentum? It's because of collisions. So whenever objects collide, it's either the particular object you are dealing with, they are going to produce, we have 2 types. We have elastic collisions and we have inelastic collisions. There is, of course, there's what we call perfect inelastic, but here you guys just stick to this. This is going to be enough for you to learn this. Do you know the difference between elastic and inelastic collisions? Under elastic, we're just saying the objects become independent after the collision. That's true. They are separate. Then under inelastic, they get attached, right, after they collide. That's what we mean under inelastic. So we're going to be discussing this. We're going to look at the first equation. So I'll give you case 1. This is in 1 dimension. So let me add this. So we say linear momentum in 1 dimension. So in 1 dimension, we have case 1 where this is elastic. So we are going to be assuming 2 things colliding. So if 2 things are colliding, we're going to say, let's say the object 1 has the initial velocity 1, then there is object 2 has the initial velocity u2. So because this is before the collision, so this is before they collide, this is moving with that, this is moving with that velocity, that's the momentum of the second object. So if something's at rest, meaning that initial velocity is going to be 0, meaning initial momentum will just be 0. But after they collide, the first ball moves with its own velocity, and also the second ball moves with its own velocity. This is after they collide. So this is the first thing, the first equation you have to learn, and this also gives us the energy preservation formula to say, now you know this was supposed to be kinetic energy initial for the first object plus kinetic energy initial for the second object is equal to the kinetic energy final for the first object and kinetic energy final for the second object. Now you know how the kinetic energy formula looks like. This was supposed to be U, I'll put 1 there, then U1 squared half m2, then u2 squared is equal to half m1 v1 squared, then plus half of m2, then v2 squared. Now there is a half throughout, so to just lessen the burden, they don't write the half. So don't be shocked if you see an equation that looks like this. And in an event where the mass is the same, meaning if they say Billand balls, if they say Billand balls, it's like those pool table balls that they use. When they say this, meaning the masses are the same, so M1 and M2 are going to be the same, meaning there won't be need for us to write the masses. We'll simply write this. So you get to be seeing this type of representation later on. So we'll just write this. This would just be the equation. Just this. This guy that looks so bare here. You've seen how it has come out, right?
Yes, I have seen how.
So in elastic, case 1, elastic, energy is conserved throughout. The energy that you get initially is going to be the energy that you have after the collision has occurred. You remember that law that says energy can never be created or destroyed, but it just changes forms. So if a car bashes into a house, the reason why the house is going to have cracks and everything else like get deformed is because the house is not designed to move. It's designed to be still. So to accommodate the energy that is from the car that hit into it, it will show that accommodation by deforming, changing its shape. But the mass, if you are to measure the mass of the house, it's still going to be the same. And the movement, it will slightly, the vibrations it will make. If you try to calculate all those, including the sound energy you're going to have at impact, everything else before and after, you'll notice that the energy input is always equal to the energy output. This is elastic under 1 dimension. You have a question?
Oh no, it's okay.
You're sure it's okay?
Yes.
Okay. So apart from this, this is under 1 dimension. So you have to be careful with the question when they mention where the object is moving. If I say a ball is moving due east, meaning you know that it's going like this, meaning take its velocity to be negative because we're going in the negative direction. If they say, why is that due west, right? This is This is west, this is east. You have north, you have south. If they say east, just know it's positive. They say this side, negative. If they say something like that, so we have to treat them the same way we're treating vectors. But here, this is under one dimension, so everything is going to be on a straight line, just either going to east or going to west. You still have to consider the sign of your velocity, whether it's going to be negative or positive.
So this one you can't choose which one will be negative or positive. They always give us.
Yes, they always give you yes. The statement will tell you.
Okay.
Then case 2 is when you have one dimension and it's inelastic. It's moving in a straight line and the guys get attached after collision. So inelastic just means they were initially independent. This is the formula here. Mass 2 V2. Then this side, they are now together. We treat them as one. So it's like object 1 gets embedded in the second object. So we're going to have this type of formula because we treat them as if it's just one particular object. It's like it's like you have a bullet coming this side, then there's a block of wood. This is before. Then after, the bullet gets stuck inside. Now they're moving together. So we're going to add the two masses. They're moving with the same velocity. So this right here is the equation we use for inelastic collision. And under inelastic, there is no energy preservation. So some energy gets to be lost. Yeah, so energy is not conserved in inelastic, unless if it was perfectly inelastic. When they emphasize to say it's perfectly inelastic, it means that, so let me just add the note. If it's perfectly inelastic, it just means in that case energy was conserved, and we are going to have say the mass and the kinetic energy of the first object squared plus the second object V2 squared is equal to half. They're now moving together, so I'll still add the masses regardless, and the velocity they're moving with is V squared, which is their V final. So that can also be the case if they say the perfect, to say this was perfect inelastic, meaning everything was conserved in terms of energy. Is this okay?
Yes, but I have a question. So if the velocities for the first and the second object are different, how do you make the when in the equal side, which velocity do you get?
What do you mean when the velocities are different? When you are saying when the initial velocities are different?
Yes.
They have to be different because they are moving at different velocities. Okay, a ball, a 3 kg mass at rest. Find the final velocity if they move together after collision. So they will always give you information about the first object. So the first object here is the mass is 2 kg, the velocity is simply 20, plus the second object is 3 kg, the mass, the velocity is, because it's at rest, so we'll take it to be 0. So this is what I mean that they have to be different. They will give you the mass and the velocities. The before information is always given. Then what you're going to be looking for is after. Because they're moving together, we'll just add the 2 plus 3. They're moving with the final velocity, which we don't know. That's the one that we are looking for. So this is now going to be 40 and 5v. Then you divide, meaning your velocity is just 8 meters per second. So they were both moving at this velocity. Now, what's your question, Miss? Can you maybe give me an example of what you mean?
Oh no, I was just wondering how we find the v like afterwards.
Oh, you mean like the final v?
Yes, that's what I was wondering about.
Oh, okay. But now this is okay?
Yes, now it's okay.
Yeah, so we add the two masses and we have that. So in the first case where there is elastic as well, only one thing will be missing at a time. Yeah, and if they make two things to be missing, that's when you have to use both equations and make simultaneous equations and solve for the missing thing. Or you make, let's say, the V final for M1 is not given and the V2 for M2 is not given. So you will also need the equation for kinetic energy. So you use this and these two. then you find the two unknowns that you have. Anyway, you look at the examples. I'll show you the examples we're going to do. The first thing that I want you to just master from this lesson is you being able to tell which case you are dealing with. Is it inelastic or is it elastic? Just based on the information that you are given in the question, you should be able to tell that. And they'll always give keywords that will be notifying. They'll be signifying. It always has to be in kilograms, and your velocity always has to be in meters per second. Now, just before we go to 2 dimensions, there's this part here that we call ballistic collision. It's like an extension of the two guys that we're from looking at, just that here it emphasizes how sometimes the bullet associates itself with objects. For example, I'll give you case 1, which is the easiest. So case 1, let's say I'll give you this. There's a block of wood which is hanging. Then there's a bullet coming this side. Then the guy will just swing. This is before, so after. Then the bullet will continue moving this side. So there is a before and after. This is the before, the mass of the bullet and its initial velocity, plus the mass of the block and its initial velocity. Mostly it's at rest, so we take it to be 0. Yeah, then is equal to, after this is elastic because the bullet just goes through, it slows down, protrudes on the other side, so it penetrates and then it's released on the other side. So the mass of the block, its final velocity, then plus the mass of the block, the bullet, you have this. This is case 1 under ballistic. Ballistic, anything to do with a bullet. These are the cases that I'm giving you here. This is okay, right?
Yes, it is okay.
Then case 2. So you notice that I also want to emphasize that in this case 1, the block is still on the same plane. It doesn't rise to a height or anything. It actually is still the same plane. This is what you have. We have the before and after. Then for case 2, it's the same thing, but then the bullet gets stuck inside and it still moves on the plane, on the same plane. Yeah, so we have something like this. Then we are having, let me say the bullet is coming there, the bullet gets stuck inside, meaning here the formula we're going to use is the mass of the bullet, its initial velocity, the mass of the block, and the initial velocity of the block, this is before, is equal to, now they are together. So the mass of the bullet plus the mass of the block times the final velocity, because they are now moving together. So this is case 2. Then apart from that, I'll give you case 3. So case 3 is almost similar to case 1, except this guy now goes to a height. It comes, let's say here. Yeah, it comes to a height. There is a height that is achieved. Yeah, but the bullet continues to move like this. Hope you see this. So the first equation you're going to write is the same one that says the mass of the bullet, the initial velocity of the bullet, plus the mass of the block, and the initial velocity of the block is equal to the mass of the bullet, the final velocity of the bullet, plus the mass of the block and the final velocity of the block. Then the second equation, this thing is swinging, it's going up, so meaning there is change in energy from, because as soon as it was at rest, in most cases it's always going to be at rest. Then the bullet comes, pushes it, so meaning it gains kinetic energy, but then it's going to come to rest at a height h. So we're saying kinetic energy is going to be converted to potential energy. This is with respect to the block, by the way, just the block. So the kinetic energy of the block is equal to this. The final velocity is equal to, this is mass of the block, and mgh, right? This is potential energy this side. So the mb can cancel, the half can cancel, meaning we can just have velocity of the block is equal to 2gh. So we have this other equation here for this case. When you make velocity of the block to be our subject of the formula.
Okay, so you're saying that for this second case, we can use any of these equations?
Yes, you can use any of them. Mostly they will go together, because the second one will help you to get the final velocity of the, because they will just ask you this question and ask you to say what's the velocity of the bullet after it passes through. but they won't give you the velocity of the block. So you have to use this one to get the velocity of the block, then replace it there. It's like, I think your question 2 on your tutorial sheet. Yeah, it's like that. You need this. This is the case.
Okay.
Yeah, so you have this. So when I give you a pair, meaning they go together in case you have two unknowns. Then the last one is, hopefully you can even guess this one. It's like the previous case, but then the bullet gets attached inside. It swings at a height, but with the bullet inside. So it swings there, but the bullet is still stuck inside. So here now we're going to say the velocity of the block and the bullet. We'll just call it V final because they're together, right? We'll just call it V is equal to 2gh because we know the mass of the bullet initial plus the mass of the block, and the initial velocity of the block is equal to the mass of the bullet plus the mass of the block multiplying what? V. So we have two equations. We have this conservation of energy, then we have also this. So we have two equations. Is this okay?
Yeah. Yes, it's okay.
Okay, so my aim today was just to give you like a preview of everything that you need. Then we'll have another session just for examples. So this is linear momentum in one dimension. This is the easiest part. Whenever they give you anything like this, you can always, it's easy to handle them. Let me give you an example before we continue. Yeah, so this question here, number 5, they're saying a 10-gram bullet is stopped in a block of wood. The mass has been given. The speed of the bullet plus wood combination immediately after collision is 0.6. What was the original speed of the bullet? So this is inelastic because the bullet is stuck, right? Is this okay?
Yes.
Because they say
yes.
It's stopped in a block. So write the equation to say the mass of the bullet, the initial velocity of the bullet plus the mass of the block, the initial velocity of the block is equal to, they are moving together. So say this and that. So capital letter B for the block and small letter b for the bullet. The mass is this. We convert 10 to kilograms. This is going to be 0.01. The velocity UB is what we are looking for. This guy was at rest. Yeah, so I'll put a 0 there because anything at rest, momentum is 0. Then if I add the mass of the bullet and the mass of the block, I'll get 5.01 kg. Then the velocity we're given is 0.6. That's the final velocity of them both moving. So now I'm having 0.01. Initial velocity of the bullet is equal to, there's a 5.01, there's a 0.6. Now in your case, you'd have to show all the units so that you see how the meters per second is going to come about. So initial velocity of the bullet is just going to be, when you multiply this, what you get.
I'm coming.
So you're getting this, which makes sense because this thing here, look at the bullet. The bullet is very light. It's like 0.01. It's like, what, in percentage form from the in comparison with the mass of the block, it's like a tenth or something. It's very, very small. So it's expected that the initial velocity of the block was very high. This is what you have, but then it gets stuck into something really big. 5 kg is very big as compared to 10 grams. So that's how the velocity of the combination of these two guys reduces down to 0.6 meters per second. Yeah, so that's the most important part of linear momentum. You being able to identify the case you're dealing with, because once you know the case, you recall the formula that you need to use. Yeah, so is this okay? This example is okay?
So it was 300.6.
Oh, it's 300.6. Okay. Yeah, so you get this. Okay, so if this is okay, let me just explain now momentum in 2 dimensions. Yeah, so there is linear momentum. So when we're dealing with linear momentum in 2 dimensions, we're just going to say there's what we call glancing collision, where the first object is moving, so this guy is moving, coming like that. Let's call this guy A. Then we have the second object. Let's call this guy B. They are on a plane. They're supposed to be on a plane like this, the X or Y plane. Then we're just saying when ball A glances on ball B, it just pushes B to go a bit high. So this is before, then after. Ball B is going to glance by going like this, simply going to, this is ball B. It's going to move this side with a velocity, let's call it V1, or let's call it VB. That's what you're going to get, because the velocity of the first, the B. Then ball A has glanced at B. Now it's going to go in the opposite direction, in the other direction down. To differentiate the angles, I'm just going to use phi instead of theta, just to differentiate them, but we're just saying they're just angles. With velocity, let's call it A. So this is technically what you have whenever there is glancing collision. And we mean to say this guy has the mass, has mass A, right? This has initial velocity A. It's moving in the x-axis. This guy is mostly at rest, but if they mention to say it is also moving like this, you have to take into consideration what the question says. So here we also happen to have the mass of B and also the initial velocity of B. We do have this, they'll give you in the question. So after they glance into each other, they just bump into each other. They don't get to stick. In 2 dimensions, it's rare that they stick. But if they stick, we'll still do the same, we'll resolve it. So like here, we're going to resolve the velocity of B into the X and the Y component. So this is going to be a VB cos your theta, the X component, and we're also going to get VB sine your theta. The same applies for the down part. Yeah, so for the down part as well, for the ball A, we're going to resolve it into VA, then cos phi, and we're also going to get VA sine phi. This is what you have. Meaning we're going to write equations in both X and, so there's going to be momentum in the X axis, which is just, this is moving in the horizontal, that's in the X. It was at rest, that's in the X. So we'll say MA UA plus MB, then UB is equal to the mass of A and the velocity of X, right, of A. The X component of A is simply that. The velocity is VA, then cos phi. Then the X component of ball B is that, so it will produce momentum in the X axis, which is MB, then VB cos theta. The same would happen even in the Y axis, so we'll say momentum in the Y, so this is 0 plus 0, because these objects are not moving in the X, in the Y. They are already initially here, before the collision occurs, they're moving in a linear, they're moving in a straight line. They're not jumping up and down. Yeah, unless if the question says so, but here, because there's no movement in the Y direction, no, we're putting 0. There's no movement in the Y direction, no, we're putting what? 0. This is initially moving in the X. They only have Y components after the collisions, these two guys. So we're going to get, this is equal to MA, then we say VA. Then we are going to get sine phi. Then you're also going to get, this is supposed to be minus, this is supposed to be, okay, let me just rewrite this. So I'm going to write the first guy first, which is simply the one for B, which is MB, VB, then sine theta, minus. The reason why I'm putting minus is because this one was going up. That's MB, VB sine theta. This one here is going down. No wonder I'm putting a negative. So this is no wonder the momentum here is negative. MA, then VA, then sine, your phi. But then we can make these guys to be equal by writing MAVA, then sine phi to be equal to MB, then VB, then sine theta. So this is the equation in the y-axis. Then this is the equation in the x-axis. They'll ask for one thing at a time. So these are the only two equations that you need when you're dealing with something in 2 dimensions. Always, these equations are always going to be like this. They never change.
Wait, so can you change the phi to theta?
Which one?
Like since it's in the sign, it's in phi, right? Can we change it to theta when calculating and keep it in phi?
Oh, the only reason why I'm differentiating this is because the angles are not going to be the same. Like Kumankala, let's say the other one is deflected at, I'm just trying to differentiate it. Let's say this was 30, then this is equal to, let's say, 25. Yeah, so you can call them theta, but just take these angles that are there. So this is your theta there, this is your phi. I'm just trying to differentiate them because they are never going to be the same.
Also, we just take the angles the way they are.
Yes, we take them the way they are, yes.
Okay.
Yeah. And that's the reason also why we're taking this guy down to be negative, because in the fourth quadrant, the sign angle is negative. Because this angle is in the fourth quadrant, right? It's like this guy. It's drawing it up. So 25 it up. So this is, so now we're taking the down part to be negative. Then this guy on top, it's in the first quadrant. They're both positive. Now we're taking them to be both positive.
Okay.
Is this okay?
Yes, it is.
Yeah, okay. So this is basically linear momentum. Now it's going to come back later on when we talk about circular motion, because the whole physics actually ends at linear momentum. Everything that we're going to start discussing after linear momentum, we're going to revisit everything in a circular path. After we're done talking about them in a rotational circular path, that's when we can move to waves, electricity, oscillations, those other things. But